Level 65 is all about what are called polyprotic acids, and these are when we have acids that can furnish more than one proton, such as sulfuric acid has H2SO4, so 2 H's, and phosphoric acid has 3 H's in it. A polyprotic acid always dissociates in what we call a stepwise manner, where it only loses one at a time. So for a diprotic acid, it contains 2 protons, which can be lost, and for a triprotic acid, it can lose up to 3 protons. So for a typical weak polyprotic acid, the Ka's, the dissociation constants, successively get weaker as you go, and that has to do with how it becomes more difficult to remove the positively charged proton. So, for example, the dissociation of carbonic acid is the H2CO3. You take out 1 proton, and you are left with HCO3 minus 1, and you can have the Ka there, given in the table. And then notice how the conjugate base, the HCO3 minus 1, becomes the new acid for the second step. And so then when you take out that second H plus 1, you're left over with the carbonate ion, and you can have another Ka for that. And notice how the Ka's do in fact get smaller. So we've just labeled those Ka1, Ka2 to tell us the step that they are. So here's table 14.4 that gives you the stepwise constants. There's also a table for Ka's given in the appendix 5.2 in your textbook, if you need to look that up. As the negative charge of the acid increases, like I said before, it becomes more difficult to remove the positively charged protons. Although you would expect the pH calculations to be complicated, they're actually not. Only the first dissociation step makes an important contribution to the H+, which then, once we solve for that H+, we can use that number throughout the rest. So we are actually going to use the numbers for phosphoric acid from this table in example 12. So for example 12, we need to calculate the pH of a 5 molar solution of the H3PO4 and equilibrium concentrations of the phosphoric acid, and then each time it loses a proton. Okay, so we are going to start with our dissociation of our phosphoric acid, where we know that it will break off by taking off 1 proton. So we'll be left with H2PO4 with a -1 charge. Okay, and the Ka from the table is 7.5 times 10 to the -3. So I'm going to call that Ka1. And so we need to figure out what X is so that we can move on, right? Just like we were doing before. So we initially start with 5 molar of our phosphoric acid and no ions. So we're going to lose from the reactants and gain from the products. So that at equilibrium, we have 5.0 minus X and X and X. Okay? And so then we're going to do our assumption to when we plug into our K expression, which the Ka1 is equal to the H+ concentration times the concentration of the H2PO4 minus 1 all over the concentration of the phosphoric acid. Okay? So then setting that up, we are going to do the assumption for figuring out X. So we have 7.5 times 10 to the -3rd equals, it's X times X on top, so X squared over 5. Or no. So when you solve for X, X is equal to 0.19 molar. Okay? Well, this tells us 3 bits of information. Okay? X is the H+ concentration, and it is the H2PO4 minus concentration, which is one of the things that we need to know. So make sure you list it somewhere that the concentration of the H2PO4 minus, we already know, at equilibrium is 0.19 molar. Okay? Well, we can figure out using X what the equilibrium concentration of our original acid will be. So to do that, to find the concentration of the H3PO4, you simply take 5 minus our 0.19, and you get 4.8, or sorry, 4.8, I was right, molar. So that's another answer that we need. So we got 2 out of our 4 answers already, which is great. Hopefully you left yourself some room, because we are going to have to write a little bit more. Okay, so I'm just going to check off that we got the H3PO4 and the H2PO4 minus. So we have 2 left to do, okay? Well, we're going to use the next Ka listed in table 14.4 for the next figuring out. So if we use our H2PO4 and minus and break that down by taking out another proton, so we're left with just one H, PO4, but now we have a -2 charge because we took away another positive. Okay, well, and the Ka for that, by the way, so that I don't forget, and we're going to label that Ka2 is 6.2 times 10 to the -8. Okay, and we can go ahead and write our Ka expression. Ka2 is equal to H plus times HPO4 minus 2 over the concentration of the H2PO4 minus 1. Okay? Well, when we're figuring in our next step, we actually know some information to plug in from our first ice chart and solving for x. When we solved for x, we knew that x was equal to 0.19. Well, I mentioned that that is what H plus is, so guess what? That's still H plus. It carries over throughout the whole problem, okay? And it's also what the H2PO4 is. So the only thing we don't know initially in our ice chart, which I'm sorry, I forgot the I, is we don't know the HPO4 minus 2, okay? Well, with this information, I'm not even going to show you the rest of the chart because looking at our Ka expression, if I plug in my information, so I have my 6.2 times 10 to the -8 equals, and I plug in what I have right now for H plus and for the H2PO4, I have 0.19 times the HPO4 minus 2 over 0.19. Guess what? The 0.19's cancel out. So this is telling us that 6.2 times 10 to the -8 is what our HPO4 minus 2 concentration is at equilibrium. So there's our 3rd out of 4 answers. All right, so then for our last step, to figure out our last thing that we need, we've gotten this one, and that one, so now we just have the PO4 minus 3 left. So we have our HPO4 minus 2 that breaks down by taking out another hydrogen, and we're left with our phosphate, which is what we're trying to find. We still know that H plus is 0.19. It doesn't change. And we just solved and found that HPO4 minus 2 is the 6.2 times 10 to the -8. Then, skipping the whole changing things because it's not going to change anymore, we can plug in the 3rd Ka, Ka3 from our table 13.4 is 14.4 times 10 to the -13. Okay, so our Ka is equal to the H plus times the PO4 minus 3 over the HPO4 minus 2. Okay, so we have 4.8 times 10 to the -13 equals, we have 0.19 times the PO4 minus 3 all over the 6.2 times 10 to the -8. Personally, I would multiply over the 6.2 times 10 to the -8 first and then divide by the 0.19. And when you do that, the concentration for the PO4 minus 3 at equilibrium is 1.5 times 10 to the negative 19 molar. And that's our fourth concentration that we need. But we do need the pH, which we have to go back and do that. So for the pH, we're going to find the pH of specifically when we know what H plus is, which H plus has not changed at all. H plus has been the 0.19 the entire time throughout all of these super long calculations. So we can use that as their concentration to find pH. So we would take the negative log of the 0.19, and when you do that, the pH is 0.72. And that is our final answer. So with polyprotic acids, yes, there are many steps, but you get a lot of numbers throughout as you go through the steps. That's why we don't have that many problems for this on homework. Note this, only in dilute polyprotic acid solutions does the second dissociation step contribute significantly to the H+. That's why we stopped doing the whole change thing in our ice charts. If you need to see more examples of this, example 14.7 on page 684 in your textbook will help you with that. And there's also a summary of the characteristics of weak polyprotic acids on page 686 in your textbook if you want to check that out too. So our assignment problems this time are numbers 106, 107, and 111.